Okay, good afternoon, everybody. So today's lecture wraps up the physics part of the course. I guess next week we'll move on to networking. And so today it's basically just some miscellaneous topics in collision detection. All right, so we've seen collision detection with axis-aligned bounding boxes, right? So all of our objects have a box around them. The axes of the boxes are parallel to the x and y axes of the world. We've seen that collision detection is not expensive. It's pretty cheap to compute if you have axis-aligned bounding boxes. Basically, all you need to do is you need to test, do the two boxes overlap? Right? If they overlap, then things become more expensive, but that's just the way things work. If your world, or if your game has lots and lots and lots of objects in it, even the testing of axis-aligned bounding boxes starts to become expensive. Right? And the reason why is because unless you have some sort of spatial data structure that keeps track of where objects are in the world, or more closely, I guess more precisely, where nearby objects are in the world, you end up having to do something like the following. So suppose your game has n moving objects. You have m static objects, so things like walls and platforms and things like that. And then if you want to do collision detection, you have to check, do any one of your n moving objects collide with any one of your m static objects, right? So there's n times m collision tests. Right? But the big problem that you run into is that you have to test, do any pair of your moving objects collide with one another, right? And so how many moving object collision pairs do you have to consider? Well, you have n objects, and you want to consider all pairs of objects, so it becomes n choose 2, right? Which is n squared in complexity, right? So if you, at every physics update, if you're doing naive collision detection, or brute force collision detection, right? Your complexity is O(n) squared plus nm, right? At every physics update, right? And remember, your physics updates are happening multiple times per second. And so this becomes a very expensive, even for axis-aligned bounding boxes, that's a very high computational cost. So is there a way that you can improve things? So one way to improve things is to use a spatial data structure of some kind. So I very quickly showed you a quad tree, which can be used to partition space. Right? So that's certainly one option that you could use. Other things you can do is that you can try to reduce this number here, right? So instead of having to look at all n squared possible collisions, is there a way that we can reduce the number of collisions that we have to look at every physics update? And so the answer is usually yes. Okay, so there's an algorithm called sweep and prune. So if two axis-aligned bounding boxes overlap, then it must be the case that their x intervals and their y intervals both overlap, right? That's the only way that you can have two overlapping boxes, right? So under certain conditions and assumptions about how your game works, it's possible to achieve O(n) expected complexity if you pay some attention to how you examine whether or not things are colliding. And so the key part here is that they overlap if and only if both their x intervals and their y intervals overlap. So what we're going to do is we're going to split up all of the we're going to split the problem into two problems. We're going to look at all of the x intervals, and we're going to look at all the y intervals, right? And so there's n of each. Okay, so this is how it works. We've got n intervals, two n intervals, I guess. So you have n intervals for the x intervals, you have n intervals for the y intervals. We're going to represent these by n pairs of real values, right? So each interval has a starting value and an ending value, right? So an x min and an x max, a y min and a y max. Right? Okay, we're going to take our x intervals and we're going to put them into a list and we're going to sort them, right? So we're going to sort them by their starting coordinate. Starting coordinate, right? And now we're going to sweep the list from beginning to end. Right, so conceptually, this is what you do. Algorithmically, you do something else, right? But conceptually, we're going to sweep this list. So I'm going to show you a picture in just a second. as you sweep the list, whenever you encounter a start point of an interval, you're going to place that interval into what's called the active interval list. Right? When you find the end point of that interval, you're going to take it out of the active interval list. All right? So if you ever find a start point, if you find a start point for some interval and the active list is not empty, then you know that the interval that you just found, whose starting point you just looked at, that interval overlaps with all the intervals in the active list. Right, and so here's a picture of what's happening. Okay, so we're going to take our intervals, so we have I1 through I5. Right, we're going to put them into our list and we're going to sort them. So I1's here, I2's over here, I3's here, I4 here, there's I5. Right. Okay, so there's our intervals put into the list. We're now going to sweep the list, so from left to right. So we start over here, we end up running, so we encounter interval I1 first. Right, so we encounter S1 belonging to I1. So I1 goes into the active list. Right, so we have an active list, so we just put I1 in the active list. Right, and you keep on sweeping the list. Right, and so now we hit E1, right, so the end of I1. Right? And so now we take I1 out of the active list. Right? So I1 comes out and our active list is empty. Right? So we keep on going. Right? We run into I3, so I3 goes into the active list. Right? Keep on going. We now hit I4. So I4 goes into the active list, right? And we know that I4 intersects I3. And you keep on going, right? So now we hit the end of I3. So I3 comes out of the active list. Keep on going. Now you hit I2, right? So I2 goes into the active list. And you know that I2 intersects I4. Right? Keep on going. You hit I5. Oh, wait, I4, sorry. There's it. Keep going. You hit the end of I4, so I4 comes out. Keep going. You hit I5, so I5 goes in. And you know that I5 intersects I2. Intersects I2, like that. And then you keep on going. You find the end of I5. Oh, wait, sorry. Keep on going. You find the end of I2. I2 comes out, right? Keep going, you find the end of I5, I5 comes out, and you've processed all your intervals, right? You have to do the same thing for the Y intervals as well, right? Everywhere where, so if I4 intersects I3 on the X axis, and it also intersects on the Y axis, then you know you have an intersection of shapes 3 and 4, right? Similarly here, right? If this is for the X axis, then on the Y axis, when you sweep that list, if I2 intersects I4, then you know that shape 2 intersects shape 4, and so on and so on and so on. Right? Okay, so there's our algorithm. Now the question is how complex is this? Right? So for n intervals, and if there are k overlapping objects, right, we have to put the intervals into the list and then sort them. So you put them into the list once, right? But then you have to sort them every time. So the sorting, we know, takes O n log n, right? We're going to do some sort of comparison-based sort, so that has expected complexity n log n. When you sweep the list, you have to look at all n intervals, so that has complexity big O of n. We're going to return the list of overlapping intervals, so that's going to take OK time, right? And so the overall complexity is n log n plus k. That doesn't quite look like ON, but it's pretty good, right? It's n log n, so not bad. So what you have to remember, so back to this picture here. So in the bottom half of this picture, these are the intervals at the next time update, at the next time step, right? So remember, your physics updates are happening very quickly. And so what that means is your objects probably don't move that fast between updates, right? So in other words, the intervals don't move around a lot in this list. So here, I2 has moved from that time to this time here, right? So I2 has shifted a bit, right? But the other intervals are more or less where they were before, right? So our list of intervals doesn't change very much between physics updates because the time between updates is small, right? And this is called temporal coherence, right? The list of intervals at one time more or less looks like the list of intervals at the next time. And so what does that mean? It means that in the next time step, if the intervals aren't sorted, right, then they aren't sorted at only a small number of places, right? So in other words, the list of intervals is almost sorted, right? And if you have an almost sorted list, well, it turns out insertion sort can sort that list in ON time, right? Expected ON time, right? So remember how insertion sort works, right? It keeps it sorts the list from beginning to end, right? And so the front part of the list is kept in sorted order, and then it considers the next elements in the list, right? So when it finds the next element in the list, it compares it to the the element in front of it, right? And it moves it down until it inserts it into the into the correct sorted location, right? So if your list is almost sorted, when it finds an element that's out of order, typically it only has to swap it with the element in front of it, and that's it, right? And so insertion sort in this case can sort these types of lists in ON time, right? And so that ON log n, the first time you put the intervals in, you have to do a general sort, so it's n log n. But every other update thereafter, this probably goes down to ON, right? And so that becomes ON plus k, which is in ON. Right? And so that's pretty neat. So you can get down to, so if you use sweep and prune, you can reduce the number of, or you can figure out how many possible collisions you have in expected ON time. Most of the time, right? There's a problem. Right? So the problem is that this doesn't work for many types of games. Right? So your performance deteriorates to ON squared if clumping occurs. Right? So by clumping, it means that many intervals, you have lots of overlapping intervals. Right? So why might this happen? So for example, you have a game, everything's happening on a plane. Right? And so all your game objects are resting on the ground at y equals 0. Right? They have all their heights might be different, but they're all resting on the ground. Right? And so what does that mean? It means their start points are all the same. Right? And so to resolve any collisions now, every time you look at an object, you have to look at the other n minus 1 objects. So now you're back in n squared complexity. Right? And so if your game is planar, right, you probably don't want to do sweep and prune. It's not going to help you. It's actually going to make things worse. No, sorry, it's not going to help you at all. Right? But if your game has, if the objects are distributed more or less uniformly across the x and y axes, sweep and prune can help you reduce the number of collisions, can help you determine the number of collisions that occur much faster than the naive method. In the assignment, you're basically using the naive method to perform the collision detection. So if you look in the physics engine code, there's a method, I forget what it's called, but there's a method that determines collisions between all objects. It basically loops, it's a nested loop over all the objects, and it tests whether any object collides with any other object. So in your assignment, your collision detection has expected complexity ON squared. Right? Okay, so there's another alternative to help you compute the possible collisions faster than the naive way. All right, so we've looked at axis-aligned bounding boxes, but we haven't considered other shapes yet. Circles are a nice alternative to axis-aligned bounding boxes for certain applications. Right? I guess the thing that I've shown here is not a good application of circles. For things that walk on the ground, like a flat ground, you probably want boxes. But if you got things floating around in space and all you care about is do they collide, then circles are a pretty good alternative. Right? So here we've got two, I guess, people surrounded by a circular bounding circle, a bounding circle. So can we use these to detect whether or not they collide? So the answer is yes. circles in particular are it's very easy to determine whether two circles overlap. Right? So here I've got a red circle, got a blue circle, a second circle over here. Right? When do they overlap? Well, you just compute the distance between their centers. Right? So it's easy to compute the distance between this point and this point. Right? You just subtract the x coordinates and square it. You can subtract the y coordinates and square. You take the sum. That's the squared distance. Right? If the distance between these 2 points is less than the sum of the 2 radii, then you know that they must be overlapping. Right? So in other words, if you compute xa minus xb squared, right, plus ya minus yb squared, right, that's the squared distance between the centers. Right? If that's less than the squared sum of the radius of the radii, then you know that they're overlapping. Right? So that's an easy test to perform. You want to use the squared distances here because square root's a relatively expensive operation. Right? So determining the collision between two circles, pretty straightforward. Right? Okay, so remember what you have to do once you've determined two objects have collided. Right? You want to resolve the collision. So in other words, you want to make sure that the two objects are no longer interpenetrating, so you want to move them apart by a little bit, right? And you also want to determine the response to the collision. Right? To determine the response to the collision, you need to know the normal direction, right? So what direction is the normal vector pointing in at the point of contact? Again, for circles, determining the normal vector is dead easy, right? So remember for the axis-aligned bounding boxes, it's not so straightforward, right? You've got to look at the four sides. You've got to figure out which sides might have collided and blah, 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 blah. It's not so easy, right? Once you figure that out, you've got the normal vector. So here, right, if you have the point of contact, calculating the direction of the normal vector is dead easy, right? So remember, the normal vector always points in the direction from B to A, right? So it's always the vector on shape B, on the second shape. And so the normal vector here, well, that's just pointing in the direction from this center to this center, right? And that direction is just CA minus CB, right? That point minus that point. So if you want the unit normal vector, you just divide by the magnitude of CA minus CB, and away you go, right? So the normal vector, nice and easy to calculate for circles. The slightly trickier part is how do you compute the dotted circle, right? So remember what happens here, right? So at the previous time step, the red circle was not colliding with B, right? So A old is the position of A at the previous time step, right? B is, for our purposes, we're going to hold B fixed, right? At the next time step, right, A and B are colliding, right? So there's an overlap here, and we want to move A back. So what we really want to do is we want to compute how much time does it take for A to move to the dotted line, right? So at the point where they just start to contact. Okay, so the question is can you do this? So if you have the old position of A, you have the old position of B, right? If B is stationary, we'll make B stationary for now to keep things simple, right? If you have the velocity of A relative to the velocity of B, right? Can you calculate how much time it takes to get to the dotted line? The answer is yes, right? It's not difficult to do. So let's see what this looks like. Oops, sorry. So we start out here. At some point in the future, right? We end up at the point of contact. So I'm going to call that CA, right? This is CB old, right? So I know that CA, it's equal to the old location of C, right? So it's the old location of C plus its velocity relative to B, right? Times some amount of time, right? And now what do I know at this point, right? Well, I know that the distance from here to here, right, is equal to the sum of the two radii, right? It's equal to RA plus RB. So I know that this distance here, right, CA minus CB old, is equal to that sum there, right? So the question is what is that value there, right? And so this is a magnitude. So if someone ever asks you for the magnitude of two vectors, one way to compute it is to compute the dot product of the vector with itself. Right, so for some vector A, right, the magnitude of A squared is just equal to A dot A. Right? So you can use that trick here. So I'm going to square this side, I'm going to square this side. Right? So I want the magnitude of CA minus CB old. So CA minus CB old. These are vectors, so I'm going to put the vector notation on it to be clear. That, right? So that's its squared magnitude. It's the dot product is so remember it's distributive, right? So you can just multiply things out like normal math, like normal multiplication. So it's just CA dot CA. Do I want to do it? Yeah, I guess I want it. Hang on, I want to rewrite this a little bit. CA. Okay, I'm now going to plug in. Oops, sorry. I'm going to plug in my formula up there for CA. So CA old plus V plus TV. Oops, TV. Minus CB old. And you want to take that with the dot product of itself. Right? So I'm just going to group these two terms here. Right? And you're going to take that with the dot product of itself. Right? So when you multiply this all out, you're going to get this dot the same thing again. So let me just call that delta C because I don't want to stop writing out that all over and over and over again. So that just becomes delta C dot delta C. Right? We're going to take this dot, this term here, which is that term there, right? Plus this dot that this term here, which is that term there. So that's just 2. 2 delta C V dot VT, like that. Right? TV dot itself. So plus T squared V dot D. V dot V, sorry. Like that. Right? Okay. You know what that is? That's just the location of the two center points subtracted with one another. You know what this is, right? We know what V is, we know what delta C is. And you know what V is, right? And so you have T squared, something times T squared, plus something times T, plus a constant equals R1 plus R2 squared. So it's just a quadratic equation in T, which you can solve with the quadratic formula, right? You throw out the negative root if there is one, and that gives you your time, right? So it turns out it's not hard to do, but you do have to solve a quadratic equation in this case. So circles also work, and they're not too bad, right? Detecting whether or not they overlap is easy. This, not so hard, but it's nice if someone works out the math for you, right? Finding the normal at the point of contact, dead easy, right? And so you can easily resolve collisions using circles as well. Okay, and so we had axis-aligned bounding boxes, right? Picture on the left, right? So remember the axes of our boxes, they're aligned with the axes of our world. Right? In many cases, you might prefer to use what's called an oriented bounding box instead, especially if the objects in your world can rotate. Right? So if your objects can rotate, it kind of makes sense to rotate the bounding box with it as well in many cases, especially if the shape is very elongated. Right? So for example, All right, so for example, suppose, I guess, someone's got a sword, right? You want to know, does the sword hit, you swing the sword, you want to know, does it hit the enemy? So, okay, if the sword looks like this, it makes sense to put a bounding box that looks like that around it, right? Now, if you can rotate the sword so that it's pointing upwards, so like this, right? You probably want to rotate the bounding box as well, so that it looks like that, right? If you don't rotate the bounding box, and you don't have to rotate the bounding box, right? But if you don't rotate the bounding box and you still want to use, an axis-aligned bounding box, the bounding box becomes very big, right? And accurately detecting collisions with this sword now becomes, is not done very well, right? Lots of space out here where the sword isn't actually hitting something, but if you use an axis-aligned bounding box, you'll have an overlap. So oriented bounding boxes make sense in a lot of cases. Right. All right, so can you detect if two oriented bounding boxes overlap easily? Right. So all we've done is rotate them a little bit. Can you do it easily? So in 2D you can. In 3D it's harder than you think. Right. And so of course a lot of the interesting games are in 3D. And so it turns out that detecting whether or not two three-dimensional oriented bounding boxes overlap is not so obvious. It's not so obvious how you do it. Right? If you do it the obvious way, it turns out your answer is, it often thinks there's an overlap when there isn't. But for 2D, you can do this pretty easily. So the trick here is that two bounding boxes overlap if the corners of bounding box A are completely outside of one edge of B, or the corners of bounding box B are completely outside the edge of one edge of A. Right? So what do I mean by outside the edge? There's probably a better way to phrase this, but I couldn't figure it out last night. Anyway, here's my bounding box. Right? I'm interested in the outward pointing normal to the bounding box. Right? So that normal vector here on this edge of the bounding box, right? That edge splits the xy plane into two halves, right? Everything above the line or in the direction of the normal, everything in the opposite direction of the normal, right? If the 4 points of your other bounding box are completely on this side of the edge, then you know that the boxes don't overlap, right? Okay. So here's a point, V1. So here's V1, right? This is on the outside of the edge that we're looking at right now. Here's a point, oh wait, that should be V2. This probably wasn't worth fixing right now, but anyway, here we go. Okay, so there's our point V1. It's outside the edge shown here. V2 is inside the edge, right? It's below that edge there. Right? How can you tell if a point is on the correct side of the edge? Right? You just look at the dot product of v1.n and v2.n. Right? So to get v1, you pick any point on this edge. Right? So you might as well just pick a corner. You can pick that corner, you can pick that corner, it doesn't matter. Right? You compute the vector from the corner to the point, and that gives you the green vector there. Right? v1.n, its sign must be positive. Right? Because it's, the angle between V1 and n is less than 90 degrees. Right? V2.n, you do the same thing. Right? Pick any point on the edge, compute the vector from that point to the point of interest. Right? Compute the dot product with n. The sign of that value must be negative, right? Because the angle between n and V2 is greater than 90 degrees. Right? So again, dot product to the rescue. Right? So what you can do is you can take your 4 points of one bounding box, of the other bounding box, test, are they on the correct side of this edge? Right? If the answer is yes, they don't overlap. If the answer is no, you can use the next edge, right? And test, are they on this side of the edge? Right? And then test, are they on this side of the edge? And then test, are they on this side of the edge? It turns out you have to do both. So you also have to look at the second box. So you have to do the same thing with the other box. Right, so for here, none of the corners of B are completely on one side of any of the 4 edges of A. Right? So on this edge, this point is on the wrong side. Right? So for this edge, that point's on the wrong side. For this edge, all of the points are on the wrong side. And for this edge, all of the points are on the wrong side. So if you just use one of the rectangles, you get the incorrect, right? This says that they overlap, which is incorrect. So you also have to look at all of the edges of, all of the points of A relative to B, right? And when you do that, you'll find that for this edge, all of the points of A are on the correct side of the edge, right? And so now you know they don't overlap. So you have to be a little bit careful about that if you're doing it this way in 2D. In 3D, it's worse. So in 3D, it turns out you can't actually perform this test. It misses some cases. It considers some cases to be overlapping when they're not. Okay, so more generally, suppose we don't have boxes, rectangular boxes. Right? So more generally, suppose we have some other polygonal shape. As long as the polygons are convex, it is possible to determine whether or not 2 convex polygons are overlapping. So this works in any dimension, but as you higher in dimension, the number of tests you have to perform become larger and larger and larger. So this is called the separating axis theorem. And so in 2D, if 2 objects are not colliding, then you can draw a straight line between the 2 objects, and that line doesn't intersect either object. Right? The corollary of that is if you can draw a straight line between 2 objects, and that line doesn't intersect either object, then you know the objects are not overlapping. So that's the trick here, right? Can you find a straight line that separates the 2 objects in 2D? The answer is yes, they're not overlapping. The answer is no, then they are overlapping. Okay, so for example, right, these are 2 convex shapes, right? There's no concave parts on these objects. So for these 2 shapes, you can just look at them, you know they're not overlapping. Right? You can draw a line. You can easily draw a line between them that separates them cleanly. Right? So this is basically an example of using the separating axis theorem. The problem is how do you find this line? Right? All right. So even if you find the line, you still have to determine, right? So I have this line. How am I going to compute that this does not actually overlap with this? Right? So one way to do this is to take this line, intersect it with every edge of this polygon, right? If it doesn't intersect, then that's great, right? I then take this line and intersect it with every edge of this polygon. If they don't intersect, that's great. You have a separating axis. There's a better way to do this, right? It turns out it's actually simpler simply to use the direction that the line is pointing in, right? So in other words, I'm interested in this direction here, and more precisely, I'm interested in the direction perpendicular to it. So I'm really interested in the direction that's normal to this line, right? And it doesn't matter which way it points in. It can point this way, it can point this way. As long as it's perpendicular to the line, everything's fine. And so here's a picture of that, right? So this is my candidate line, my candidate separating axis, right? The green vector is the vector perpendicular to the line, right? If you project the points of both polygons onto this axis here, right? So that's the direction that the green line is pointing in, the normal vector is pointing in, right? I project all these points down, then the range of these points is from here to here, right? If I project all of these points onto the green axis, right, then the range of those points are from there to there, right? And so in this coordinate system, so if you imagine that green line is the local x-axis, right? I know that the max of the red values is less than the min of the blue values. Therefore, the 2 intervals are not overlapping. Therefore, the shapes don't overlap. Right? So the question is how do you project these points from the red polygon onto that axis there? Right? Well, that's just the projection. Which again is just the dot product, right? So what do you do? So if that is n, Okay, so let's actually draw this out. So I've got a shape here. I've got 4 points on my shape. I'm just going to draw the x and y axes somewhere. It doesn't matter where they are, right? My separating line looks like that. And so my normal vector looks like, I'm going to make a point the other way because it's a little bit easier in this example, like that, right? What I want to do is I want to project these points onto an axis parallel to that, which I'm going to put here. Right? So this is n, that, right? Right? So this is pi, right? One of the corners on that point, right? If I want to project that point onto this axis here, it's just the projection of pi onto n. Right? So it's this distance here, right? And so the projection of pi onto n right? Remember, that's just pi dot n. If n is a unit vector, right? That's a scalar value, right? And so it's just that value there, right? Which is, in this case is positive, right? You're going to do this for every point here. So that's the projection of that point, right? And so on and so on and so forth, right? And so what you end up with, you find the min over all of your points I of pi dot n. Right? So you just compute the 4 projections, right? You take the smallest of them. That's this value right here. Right? Technically, it's this value right here, right? And then you find the max of all of those. Right? And that's this distance here. So that gives you an interval from there to there. Right? You do the same thing with the other shape. Right? You get the interval for the other shape. Now you just test if the 2 intervals overlap. Right? And that's the separating and that's how you compute whether or not the two shapes overlap once you have the axis of projection. So how do you get the axis of projection? So in 2D, it turns out that you can just use the edges of your 2 shapes, right? So here I've got here we have 2 triangles. And so in this case, there are 6 possible axes that you have to consider, right? So there's the axis given by the E1, right, on the blue triangle. There's the axis given by E2 on the blue triangle, and E3 on the blue triangle, right? Similarly, E4, E5, and E6 on the red triangle, right? And so you can see the projections, they're all drawn up here, right? So when you project onto E5, or onto the direction perpendicular to E5, right? The red triangle is here, the blue triangle is here. It looks like they overlap, right? But when you project, which vector is this? So when you project using E3, right, onto the line E3, you end up here and there, right? And they don't they don't overlap. And so that blue edge, E3 of the blue triangle, gives you a correct separating axis. So it turns out in 3D it's much worse than this, unfortunately. You have to use the faces of all your shapes. You also have to consider the cross product of every face normal with every other face normal on the other shape. And so if your shapes have lots of faces, it becomes hard to, it becomes more computationally expensive to use the separating axis theorem. It is often used, though, to determine whether or not 2 oriented bounding boxes in 3D overlap. You have to be very careful about how you implement it. There are standard implementations out there that take great care in how they do the calculations. All right, so we've got circles. We know that circles work. We've got oriented bounding boxes, which are just rotated rectangles, right? Can you have a rotated and stretched circle? So can you use ellipses as bounding shapes? Right? You might want to use an ellipse because, again, instead of having a circle around an object, you might have a very elongated object, in which case an ellipse would be a better fit, possibly a better fit. Right? So can you use ellipses? The answer is yes, you in fact can, but it's probably impractical for gaming purposes. In 2D, you can do it. Right? Okay, so what do you have to do? Well, I have to determine, do the two ellipses overlap? Right? And so it turns out that is not as easy to do as you might think. It turns out it's sort of hard. The answer has been known for, for some time. So to determine whether or not they overlap, it's possible to do. Once you've got them overlapping, you want to compute this distance of closest approach, right? So you know which direction one object is moving relative to the other. You want to find out how much time elapses until they just touch. So in the scientific literature, that's called the point of closest contact. And so for ellipses, people thought that there was no way to write down the answer for this. Right? So the thought was that there was no analytic solution for this problem. Right? So there's no equation that tells you where is the point of contact, how much time does it take for this to occur. 2007, someone actually figured out that there is in fact a way to do this. Right? So not that long ago. And so the paper that does that is here. Right? So it's the distance of closest approach of two arbitrary hard ellipses in 2 dimensions. Right? Did this come out of the game literature? No. It came out of physics. Right? It came out of crystallography. And so this is written by a mathematician and a physicist. Right? And so it turns out there's lots of problems that show up everywhere. This is one of them that happens to show up in a lot of places. Right? So 2007, they actually figured this out. So it turns out you have to solve for the roots of a 4th order polynomial, which you can do. There's an equation for the roots of a 4th order polynomial. Before this paper came out, everybody thought you had to solve for the roots of a 5th order polynomial. There is no equation that tells you what the roots of a 5th order polynomial are. And so everybody thought you couldn't do this analytically. Turns out you can. And so in 2D, if you want to, in principle, you can use bounding ellipses. It's probably not practical. In 3D, you would want to use bounding ellipsoids. There, it's known there is no way to calculate the point of closest approach analytically. Right? It's the roots of a 6th order polynomial. There is no general equation that gives you the roots of a 6th order polynomial. And so bounding ellipsoids, probably not using them, at least not for video game purposes. Right. All right. And though there are some random pieces of information about collision detection, and that wraps up, I think, our discussion of physics and game engines. There is a lot more to learn. So there's many books. So first of all, there's an entire book on real-time collision detection. It's like 700 pages long. The title is Real-Time Collision Detection, if you are interested in looking at it. Right? And so that's just the collision detection aspect of the physics. Right? All of the other stuff, modeling cloth and fur and hair and other things like that, all of those, there's lots and lots of resources that you can look at. There's many, many unsolved problems in those areas. Right? All right, I guess that's all I want to say for today. I guess next Tuesday we'll start talking about networking in games.